This is problem 74 from chapter 17. In this problem, the 5-kilogram cylinder is initially at rest when it is placed in contact with the wall B and the rotor at A. If the rotor always maintains a constant clockwise angular velocity of 6 radians per second, determine the initial angular acceleration of the cylinder. The coefficient of kinetic friction at the contacting surfaces B, which is between the wall and the cylinder, and C, that's between the rotor and the cylinder, is 0.2. So we have the same coefficient of kinetic friction for both of those surfaces. Equations 17, 14, and 16 tell me I can apply Newton's second law in this situation and also sum up the moments either about point G or about point O, and that's equal to the moment of inertia times the angular acceleration. In this problem, rather than using Newton's second law with normal and tangential components, I am going to use x and y coordinates. Before I go any further, I'm going to turn to the back of the book and find the moment of inertia for the cylinder. So for the cylinder rotating about an axis z, which goes through the mass center of the object, the moment of inertia is 1/2 the mass times the radius squared. For the cylinder, the radius is 125 millimeters. So for the moment of inertia about the mass center, we get 1/2 times the mass of the cylinder times 0.125 meters squared. The next thing that I'm going to do here is draw a free body diagram for this situation. And we have contact forces and non-contact forces. The only contact force we have here is the force of gravity, which acts downward at the mass center. Then the other forces I have come from things that are touching the cylinder. We have the wall touching the cylinder that exerts a normal force on the cylinder and also a frictional force. The normal force is perpendicular to the surface of contact. And if the rotor is rotating in the clockwise direction, then the cylinder is going to rotate in the counterclockwise direction. So if the cylinder is rotating in the counterclockwise direction, we have the force of friction acting upwards. And that's the friction that the wall exerts on the cylinder. And then we have the rotor touching the cylinder, and we have a normal force, and they give you the angle here is 45 degrees. So this force is at a 45-degree angle from the negative x-axis. And we also have a force of friction. And when you're figuring out the direction of the force of friction, you ask yourself what the object would be doing if there was no friction, or friction opposes the motion here. So you have the cylinder rotating this way, so friction's opposing the motion and going upward. But when you look at the surface between the cylinder and the rotor was initially at rest. So the reason that it's moving now is because you have a force of friction which is being exerted on the cylinder from the rotor. And because the cylinder is initially at rest, and then it's going to speed up, we're looking for the angular acceleration. If you look at a point on the cylinder here and a point on the rotor, those points are not moving together to begin with because the rotor is already rotating and the cylinder is at rest. Okay, so because the cylinder is going to start to speed up, we have friction acting this way, which is going to cause the cylinder to rotate in this direction. So we have our free body diagram here, and I can add this angle in. Also, this is 45 degrees because this is 45 degrees. And when I sum up the forces for Newton's second law, I'm looking at the mass center, which is here. This is point G. The cylinder is rotating, but the mass center is not translating, so the acceleration of the mass center is 0. So the sum of the forces in the x direction is equal to 0, and the sum of the forces in the y direction is also equal to 0. So I'm going to start there. I could start by summing up the moments about point G and setting it equal to the moment of inertia times the angular acceleration. But when I do this, I'm going to have the unknown forces, the unknown normal forces in this equation. And so I would not be able to finish solving for the angular acceleration until I look at Newton's second law. Okay, so now we're going to sum up the forces in the x direction and also in the y direction. sum of the forces in the x direction is equal to 0. This gives us, if we look at the forces acting in the x direction, I have the normal force here from the wall, so that's normal force B, and the frictional force does not have an x component. Both of these forces have x components, and because the angle is 45 degrees for both of those forces, I'm just going to say this. Cosine of 45 degrees is equal to sine of 45 degrees, and that's equal to 0.7071. So I'm not going to worry about whether it's a cosine component or a sine component, and I'm just going to stick the 0.7071 in there for cosine of 45 degrees or sine of 45 degrees. So both of these forces have a component in the x direction, the normal force that's acting to the left, the frictional force that's acting to the right. This force was acting to the right and we called it positive. So if this is positive, then the frictional force has a positive x component, so that's plus 0.2 NA times 0.7071. This force has a negative x component. That was an A. So that's minus NA times 0.7071, and this is equal to 0. Now I'd like to rewrite this by solving for NB, so I'm going to bring both of these over to the other side, and on the other side of the equation this would be positive and this would be negative. I can pull out an NA times 0.7071. This is positive, so that's 1 minus 0.2. So that's NA times 0.7071 times 0.8, and that gives me 0.5657 NA. And we're going to call this equation 1. Then I can look at the sum of the forces in the y direction, which is also equal to 0. In the y direction, I have my frictional component for the my frictional force between the wall and the cylinder acting upwards. So that's 0.2 times NB. Then I have a component of the frictional force between the rotor and the cylinder, which is also acting upwards, so that is 0.2 NA and 0.7071 for the upward component. And this normal force also has a component acting upwards, so that is plus NA times 0.7071. And then I have the force of gravity acting downwards, and so that is minus mg. That's equal to 0. Now, let's simplify this a little bit, and we can combine these, and that's NA times 0.7071. Then I have 1 plus 0.2, so that's 1.2 for these two terms added together, minus mg is equal to 0. Well, let's call this equation 2. Then I can take what I have for equation 1 here, and I can put that in for NB and solve. And I'm going to let you do the solving on your own. We know the mass is 5 kilograms, so you can put that in here. And solve, and you should get NB is equal to 28.85 newtons. And then you can use the NB that you find to go back to equation 1 and find NA. And you should get NA is equal to 51.01 newtons. Okay, so we did some of the forces in the x direction and some of the forces in the y direction. Now I can do the sum of the moments about point G. Okay, remember when we learned about some of the moments back in chapter 15? It's the vector r crossed with the force, and the vector r goes to the point you're looking at from the point about which you are summing up the moments. So, I look at the forces at point B. That would be the vector that I'm looking at. And you're doing the cross product, so when you cross this vector with the normal force there, you get 0. When you cross this vector with the frictional force for the cross product, you get something pointed in the negative k hat direction. And so this is negative. The magnitude of this vector is just the 0.125 millimeters. 0.125 meters. And times the frictional force, that's 0.2. Let's just put in NB. And we know NB is equal to 28.85. And it's negative because for the cross product, that's pointing into the page. And then if you look at point A, your vector r is going to point A from point G. And when you cross that with the normal force, you get 0. When you cross it with the frictional force, you get something pointed upwards. So this is positive. And the length of the vector is 0.125. This is crossed with the frictional force, so that's 0.2 times NA, and this is equal to the moment of inertia times the angular acceleration. These are pointed in opposite directions because this frictional force is causing the cylinder to speed up, but this frictional force is opposing the motion of the cylinder. Okay, so now I need my moment of inertia. This mass is 5 kilograms, and so if you plug that in, you get for the moment of inertia 0.03906. So there's our moment of inertia. And we have the normal force is between the wall and the cylinder is 28.85, and between the rotor and the cylinder is 51.01. So taking these and plugging them in here and solving for alpha, we get 14.18, and this would have units of radians per second squared. And that concludes problem 74.